Hello and welcome to the next series of lectures on generative models. Specifically, we'll begin with generative adversarial networks. Here is the outline of this module. We will begin with an introduction to generative models, look at some basic concepts in generative models, and of course, we will explore generative adversarial networks. Okay, so we will now talk about generative models, specifically the difference between discriminative and generative models. So, what is the definition? As stated here, it's generative model is a statistical model that actually learns the distribution of the data set in order to generate new but not the same data that is in your data set, right? So, these are synthetic samples which are similar to the original data. So when you say data set, the data set is your training data. And of course, it does not include all possible data of that type, but a fairly large collection of the type of data that you would want to model. Okay. And the idea is to figure out the process by which the data originated. Okay. So that's one way of looking at it. If you're all familiar with the classification models. You have looked at it so far, looked at image classification specifically. So the idea here for a generative model is to model the joint probability distribution, that is P of x comma y. Model both the label as well as the data distribution, the joint distribution of these two, and from there generate synthetic data of certain belonging to certain classes. As the name suggests, the whole idea behind generative models is to enable the synthesis of new data samples which are similar to the data set in your training data, similar to the data points in your training data, but are not present in there. Okay, but the general idea is you want to create new types of data not seen in your training data set. And the way to do that, it turns out, is by learning a so-called latent space representation of your data, which is a compressed and meaningful representation of the data. So when I say compressed and meaningful representation, it means that if your original data, let's say, is images, they're let's say 1000 by 1000 images, right? 1000 plus 1000 2D images. You can learn a, let's say, 512 dimensional vector representation of those images for every image in your data set, that is, which can compresses all the information in your actual data, and sampling from that latent space can help you generate new data sets, new data points. Okay, so why are these generative models so powerful, right? So we are just, as the name suggests, they are able to generate new data, but that's it's a very narrow way of looking at it. So what are the capabilities that you generally would attribute to generative models, right? So the first one is, of course, to be able to generate new realistic samples, right, which are very similar to your data set, similar to the ones in your data set, but not exactly the same as those in your data set. Helps you understand the data, that is, you can extract these so-called latent structures and their dependencies within the data. Sometimes they are interpretable. In the context of deep learning, the latent structures are not exactly easily interpretable. You can use these models to fill in the gaps in incomplete data. So a very straightforward example is you have an image with a hole in it. You can use this for filling in the holes. Okay, so you can call it inpainting, for instance. Anomaly detection. So once you have modeled your data, that is, you have got the probability distribution of your data set, then you can use that to identify data points, just data points that are not from that distribution. So these are basically anomalies that you can detect. Now, not all models can do that P of x. For instance, x is your new x test is your new data point. P of x test, if it's very small, you can say it's an anomaly. But most models are not able to do that directly. But there are indirect ways of doing this. Because finally, but most important is representation learning. That is this is where this is the real power of these type of models, is to discover these latent representations which are low dimensional and meaningful, and they can be used to generate new data. Okay, so how to do this? This forms the crux of these generative models. Okay, so let's start with a small example, right? So to understand what we mean by what is meant by generative models. So it's not very straightforward. So for instance, consider a very a small image, 2x2 grid of pixels. So this is your what do you call data set? You can call it a training data set. It's 2x2 grid of pixels, right? And each pixel can either be black or white. So black means background. Background pixels typically you denote by 0. When it's put on the screen, they appear dark. Foreground pixels usually take on the value 1. So when you throw them on the screen, you display them on the screen, they appear bright. So these are grayscale 2x2 grid of pixels. So what are the possibilities? So if there are four locations, pixels locations, which means there are totally 16 possible images. You can actually enumerate them. If you rasterize the image, you can write down all possible combinations of 1 and zeros corresponding to 4 positions, right? And therefore there are 16 possible combinations. Here is an example image, right? So for instance, the top left is 0, 1, top right, and bottom left is 1 again, bottom right is 0. So you can actually enumerate this or list this image as 0, 1, 1, 0. Okay, so like that you can write down all the possibilities. You will end up with 16 possibilities, right? So let's assume that we have this data set of 2x2 images. Okay, what would a generative model do? Generative model would then try to learn this probability distribution. That is what the probability of x11, x12, x21, x22, where xij is the pixel value at row I and column j. So here, if you see, we are not letting go of the pixel locations, because without location, it doesn't mean anything. An arbitrary collection of pixels cannot make an object. So in this case, it's a toy model, so it's not directly applicable here. But let's say you're looking at images of cats. An arbitrary collection of pixel values cannot lead to an image of a cat, right? So you have to attach them to their coordinates also. Then this is what is done here. The way you do that, when you specify the let's say probability distribution, is to rasterize them in a certain way or vectorize them in a certain way. In this case, it's you are taking one row at a time and then making them into a vector. So this is the probability distribution that we are trying to learn. Again, xij is the pixel value at row I and column j. Now for this case, there's a reason why we did this case. It's a very simple case where we can actually simply count the occurrences of each of the 16 possible images and normalize them. So you can go ahead and collect all occurrences of these 2x2 images where the pixel values are 0 and 1, and you can count the occurrences of each type of them. And what do you mean by each type? Let's go back to the previous slide. We saw this picture, right? So how many of this occur? Maybe there's a different combination where top left is also white, and then you count the number of times that occurs, and then once you have all the counts, you can normalize them with the total number of images to get a probability value for each one of these variations, right? So that's what we would like to do, right? So for a small grid like 2x2, we can actually explicitly enumerate the probabilities, right, for each of the 16 configurations. So for instance, these are the possibilities. All white is 0.3, even diagonal black is 0.2, checkerboard pattern is 0.1, so on and so forth for all the 16 states. In fact, this is possible primarily because it's 2x2, it's a very small image, and there are only 2 possibilities for every pixel. But for real images, the number of pixels is huge. So for instance, a very small nominal RGB image would be 256 cross 256 cross 3, and each pixel can take values from 0 to 255. So in that case, making this enumeration is very hard. Okay, so this is where generative models, like the ones we are going to study, come up with some very clever methods to approximate this kind of high dimensional distributions. But we'll consider this 2x2 and then see what generative models are, what they can do in this context, and also get you an understanding of what generative models are. Okay, so once a model has learned P of x, right, and then what do you do with it? So we can actually sample from it to create new data points, right? How do we do this? So for instance, in our 2x2 example, if we know that the diagonal black pattern that we are looked at is common, Then if we also know the probability distribution, and if we, let's say, sample the most probable point which would correspond to a diagonal black pattern, that is most likely the image we would generate. Okay, so this would be a sampled image. Why would this be? Because we know that this occurs often, therefore the probability of this particular image is very high. Therefore, when we sample from that distribution, we'll end up sampling an image like this. Okay, so let's just do this, some examples numerically, just so that we understand what we mean by generative model, what do you mean by distribution, so on and so forth, so that we understand what we are doing. So let's just do this numerical example, 2x2 grid. So top x11 is the top left. Okay, so 1 is the pixel value 1 would correspond to white, 0 would correspond to black. So we want p x11 equal to 1. Okay, so which is basically we want the probability that the top left pixel is white. Okay, so since we know that regardless of what other pixels are. Okay, so that's what we want to find out. Okay, so then so the idea is the following. So how many images exist such that p x11 equal to 1? There are 8 possibilities, right? Because x11 can take either 0 and 1. There are 16 possibilities, so 8 of them would correspond to p of x11 equal to 1, and all you have to do is sum the probabilities of all these 8 images where x11 equal to 1. So let's look at this hypothetical joint probability, right? So once again, these are just arbitrarily chosen numbers. Okay, if you write down all 16, they should sum to 1. Remember, that's what the probability distribution is. And while we are looking at this is again something that I would like to point out here, is because if you look at this, p of x11 equal to 1, x12 equal to 0, x2, this checkerboard pattern occurs with all these configurations. This configuration here corresponding to that 1 0 1 0 pattern has very high probability. So if you use this distribution to generate a picture, right? How do you generate an image? You will end up have to sampling from this distribution. The way you would sample is to find out what is the sample that corresponds to the maximum value here, 0.15. Therefore, this would be our generated image, right? So that's basically what you would do. You try to see what is the configuration that corresponds to, in this case, let's say the mode of the distribution. So but then they are looking at the possibilities here where x11 equal to 1. So these are the possibilities, 8 of them. And if you want to calculate this probability that p of x11 equal to 1, you just have to add up all of them, right? So what is marginalization? This is marginalization, right? So you have to integrate over the other variables there, which are the other pixel location, the values are the other pixel locations. So the marginalization here means finding the probability of a subset of the variables by summing over the others or integrating over the others. If you're working in the continuous domain, here we have discrete events 0 1, so we will just sum over them, right? So if we have p x1 x2 x3 x4 on our 2x2 grid, then to find the probability p of x1, that is, let's say for instance the top left pixel being black, we do that over all possible states of x2, x3, x4. Okay, so this is basically what we have to end up doing. So probability of x1 is just this. Okay, so once again, this is a very or in this case I would say, in fact I should have said the probability of top left pixel being white. Typically that's what we would we end up specifying for p of the values being equal to 1, right? So that's what we usually end up specifying. That's okay. So that's p of x1 is what we would specify here. So all we do is marginalize over this, and when we do this for this particular configuration, we will end up putting from somewhere around 0.5. Okay. So what does this tells us? This tells us the overall likelihood of a specific pixel value, right? So, and it's regardless of the other pixels. What is the probability of px1 equal to 1? Regardless of what the other values or the other pixels takes, right? The values taken by other pixels, that is x2, x3 and x4. So the other application would be inpainting, right? So if you are looking at parts of an image, let's say parts of an image are missing, that is some pixels are unknown. So you can use a generative model to fill them in. So generative model, quote unquote, can generate the missing pieces. So how does it do that? Again, this is done by doing a conditioning on the known pixels. So you formulate the conditional probability of the unknown pixels given the known pixels, and then generating the most probable values for the missing ones. Okay. So for instance, if you have a partially observed image x OBS, that's x subscript OBS, and the missing pixels are x MAS, we want to find out this probability. What is the probability of distribution of this given the observed data, right? So, and you can use Bayes theorem to end up with this observation, wherein P of x missing given x observed is the joint distribution of x missing and observed, which is basically your entire the model. That's what we want to estimate. And the numerator is P of x observed. P of x observed is again gotten by marginalizing over the missing pixel. So that's basically that's what we saw. That's marginalization trick we saw earlier. It can be used here. Now for a 2x2 grid, if we know that the top left pixel is black and the others are unknown, let's say, the model can easily predict the most likely full image. So let's say the top left pixel is white and others are unknown, then the model can predict the most likely full image, right? So, so let's assume, for instance, that we have learned the full distribution of all 16 possibilities of the 2x2 binary image, right? In our input image, we have only one known pixel, that is x11 top left is white and there are 3 missing pixels, okay? So what we want to do is fill them in, right? How do you fill them in? We want to find the most possible probable configuration x12, x21, x22 given that x11 equal to 1, okay? So this is exactly what we would like to do for this in-painting example. So this means that, so what do you have to calculate? We have to calculate probability of x12, x21, x22 given x11 equal to 1. Again, this is considering 2 raised to 3 or 8 combinations of the missing pixels, right? So it's not too hard to see. So again, we go back to the formula where the joint we model this distribution. Probability of x missing given x observed is the joint probability, which is again the probability, the distribution of the data divided by the probability of x observed, which we get by marginalizing over the missing pixels, right? So the denominator is just P of x observed if we do that, and it is constant for all candidates. So we don't, it is a constant number. It doesn't really change based on what is there in the numerator, so we can just let go of that. So we just have to find out the argmax of x, argmax x missing of of P of x missing comma x observed, right? That is what is like the most possible, what is the configuration that is the missing pixel configuration corresponding to the highest value of this probability, or that is which combination of x missing would maximize this probability. That's what we are going to find out. That's all we need to find out, right? So we just can use a hypothetical joint distribution, okay? Once again, we have listed some of them, okay? This, of course, there are 8 of them listed where x11 equal to 1, and we can list 8 more where x11 equal to 0. We have to make sure that they are properly represented in the sense if they add them, you should add to 1, okay? So you just have to make sure of that. What we are trying to look for is this configuration. What is x12, x21, this triplet that would maximize P of 1, x12, x21 and x22. So once we do that, so from our list, if you look, this is the maximum, okay, of this. Whenever x11 is 1, this corresponds to maximum. Therefore, our completion, most possible probable completion is 0, 1, 0. This means black, white, black. That's what we want to fill in with. That's exactly what we will fill in with, okay? So this is the in-painted output. So just by knowing this distribution of pixels, we are able to solve this in-painting problem. Similarly, we could solve probability of certain pixel, distribution of a certain pixel given, by marginalizing over all other values, right? So that is also a possibility. So this model was able to fill in just by using the distribution. That is basically what is, something that you have to keep track of when you want to understand generative models. Having the P data or the model or the probability distribution of your data can help you solve a variety of tasks. Something like, for instance, in painting in this example. So what happens, when we start increasing the size of this data, right? So our 2x2 grid, it has we had 4 pixels. So if 3 are missing, let's say it's very simple math, we just check 8 combinations. So that's trivial. So let's say a very small real world, this is not even real world, 32x32 is not exactly real world, but let's say this, consider even 32 cross 32, that's like 1024, 32 and 32 is the total number of pixels is 1024, 32 and 32. So that means the total number of possible images is 2 raised to 1024. If you are just considering binary pixels, right, 0, 1, but then you can also imagine color pixels, and this is basically astronomically large. Okay, it's a very large number of images. So even, and if you're trying to figure out, like say in the case where half the pixels are missing, right, and then that would mean that we need to marginalize over 2 raised to 512 possibilities for the denominator, or check about 2 raised to 512 candidates for the numerator, which is really very difficult, right? Computationally impossible for explicit this kind of enumerative generative models. Okay, so the way that modern models work is that they do not explicitly learn, or they do not just learn p of x directly, right? Or they don't store that joint probability table. Instead, what they try to do is learn a function to approximate this distribution, or learn a function to sample from it, or generate samples from it, right? So basically for inpainting, you would use these functions to sample iteratively, right? Start with random values for mixing pixels and iteratively refine them. Directly predict. So for instance, a neural network in diffusion models, which we'll learn later, basically train to directly predict the missing pixels, right? Finally, latent space manipulation. So for the models that we're going to start looking at, variation autoencoders and specifically GANs, inpainting can involve basically you encode the partial image into a latent space, and then manipulate the latent representations to and then decode the latent representations to generate the full image, right? So all these methods that we looked at, that is GANs, VAs, diffusion models, they avoid this explicit table joint distribution, joint probability table, right, of all possible combinations. So that's why inpainting is feasible when we have very large high resolution images. So we have to look at one more application, which is classification, right? So here, this is something you have looked at already with CNNs. We input an image, and the trained CNN will indicate the class of the image. Now, but we can use a generative model for this purpose also. So for instance, if we have generative models for each class, that is pure probability of x given y equal to a certain class, we can use them for classification. So how do you do this? Given a new input x, we find the most probable class y. That's not too hard to do because we have the distribution. So using Bayes theorem, we can actually rewrite probability of y y equal to c, the class belonging to c given x. That's what we want to find out. And knowing this distribution, the generative distribution, we can directly estimate it. So how do you do that? We choose a class. Our idea is to find the class that maximizes the numerator. As p of x is a constant, so we conveniently ignore it. So something that maximizes the numerator is what would yield the classification network, right? So we can use generative model to do classification also. Of course, we need a very good idea of what p of y equal to c is. This is a generative classifier, right? And you will come across this also a lot when you start looking at generative models, right? There's another thing. Generative classifiers like probability of x given y and along with the probability of y can be used to generate data, right? So to some extent, the algorithms have listed here, the models have listed here, and some types of neural networks can also generate data, right? Naive Bayes, latent LDA, latent Dirichlet allocation, etc. Discriminative classifier, what does it do? That's what you have learned so far. What is the discriminative classifier? All the CNN models that you have learned so far probably outputs p of y given x. If you look at, of course you must have looked at it when you did the image generation, image classification. What the network does is to output a probability distribution over the different classes, and that probability distribution you can interpret as probability of y given x, this conditional distribution. Okay, all it does is learns the decision boundary. So all of these algorithms here do that. That is logistic regression, support vector machines, standard neural networks, even the CNNs. So, but then why do we need the generative models? As it can do all of these above applications which cannot be done. Some, of course, other than the classification, the discriminative models cannot generate new data, right? Another advantage is that they are more robust to missing data. How? Because you can always marginalize over it, and it provides richer information in the sense you can do a lot more inference. But at the disadvantages, you require a lot of data to learn P of X given Y accurately. Okay, so here are some examples. Sora 2 generates videos from text prompts. Imagen 2 from Google. I think this is an OpenAI in Google. Imagen uses text prompts to generate realistic images. Also offers editing capabilities. Stable Diffusion, again, very widely used open source model, can actually produce images with very fine detail, and of course it's community supported. Text to audio, audio gen, state of the art model, which gives you high fidelity audio samples, sound effects, etc. from text descriptions. Okay. So over the next videos, we'll look at the mathematical formation and other details of your typical generative model.